I said in the last few videos that we will restrict our analysis in this class to only a two-dimensional analysis of two-dimensional objects. But in reality, there's no such thing as a two-dimensional object. When I say we'll be modeling two-dimensional objects, I mean we will be taking three-dimensional objects, but only three-dimensional objects that we can model in two dimensions. There's a couple different situations where we're allowed to do that. The first is if we assume that our object of interest is a thin object, a uniformly thin object, and that all of the forces are applied in the x and y direction in such a way that the only components of stress we have are stress in the x direction, stress in the y direction, and shear stress in the xy direction, and that there's no component of stress in the z direction. That is to say that the stress in the z direction and shear stresses that include a z component are all equal to 0. This is referred to as plane stress. The other situation we're allowed to model in two dimensions is a situation where we have a long, narrow object and that all of our forces are applied either in the x and the y direction uniformly, so that any force I have here applied in the x direction is applied uniformly along the x direction, and any force in the y direction is applied uniformly in the y direction, in such a way that any deformation of this object is going to be the same no matter what slice of the object I select. In this case, I will have components of strain in the x direction, component of strain in the y direction, and shear strain in the x, y direction. But I'm assuming all of the strain that has a z component is 0. So I'm assuming that the normal strain in the z direction and the shear strains in the zx and the shear strain zy are all equal to 0. Now in this case, you'll remember the last video, I showed you a large 6x6 matrix I labeled the D matrix. This is a matrix that relates the 6 components of strain to the 6 components of stress. And remember, I'm forming that out of just 6 equations that relate the 6 components of strain to individual components of stress. Now, in both of these cases, I only have 3 components of strain and 3 components of stress. So this matrix simplifies. It's the same matrix. It's just that a lot of these terms, if I know, are 0, and a lot of these terms I know are 0, I can rewrite this matrix in a simpler form. I'm making different assumptions of what terms in this equation are 0 for plane stress as I am for plane strain. So I'm going to get 2 different versions of a 3x3 simplified D matrix. So I get this form of my D matrix if I'm looking at a problem that I can model as plane stress, and I have this version of the matrix that I can model or use if I'm allowed to take my 3-dimensional model but model it as a 2-dimensional plane strain model. Okay? So these are the 2 different versions of the D matrix that we'll be using. You don't have to worry about confusing them because you'll decide early on in your problem solving whether you're taking an object and modeling it as plane stress or modeling it as plane strain.